Good day. Welcome. What's going on? I'm going to try to record this and get the one with good quality sound, so I'll denote that as we go. Hopefully no sound issues with today's production. The mic nice and close somewhere else. So we're going to talk about differentials, and there's a couple of different things with differentials, a couple different definitions that you will see right here on this particular slide right there. It's, for one thing, it's an alternate form of the derivative. And it's a method that we use to approximate values of the function. We'll get into that one and probably one more before we're done. So here we go. All right, so there it was. It's easy enough that I don't need to say a word. You can get the picture. You know how to take derivatives, and it's just an alternative form. But now we'll talk a little bit about linear approximation and what it actually means. So if I've got some sort of function, okay, and I've got its derivative right at that particular moment, so pretend that red line's the derivative. If I zoom in on the function enough, right in this little region here, if I zoom in, zoom in, zoom in, zoom in, no matter how curvy it is, eventually I can get to a place where it appears to be a straight line. That's called local linearity. So if you zoom in enough on a function, it's locally linear. So what we do to approximate things is we use that fact that, well, you know, for the most part, we're looking at a straight line. So if I want to know, like, say, for instance, this is probably, you know, way too far off the mark. I want to know what the value of the function is right here at the at x plus delta x, and I know what the value of the function is here at x, so I know the f of x, I can use the derivative and multiply it by dx. Because think, you know, in terms of local linearity, this is like change in y over the change of x. If I multiply that by dx, I've just got the change in y left, right? Those are gone. So if I take the value of the function, I add how much y changed by, I've got the new value. All right, so this kind of here represents how much my dy changed. We'll do an example or two, and you'll see exactly what I mean, hopefully. So if I want to use differentials to find the square root of 26, now I know you're thinking, well, I would just put that in my calculator, and yes, you would, but for the sake of argument, we're going to do it this way. All right, we're going to use the fact that the f of x plus delta x is approximately equal to the f of x plus f prime of x times dx. And we know that the function that we're using is the square root of x, which we also know is x to the 1/2. And we further know the derivative of x to the 1/2 is 1/2 x to the negative 1/2, or 1 over 2 root x, or 1 over 2x to the 1/2. Whichever way you like, we'll use root x because, well, that's what I wrote there already. Okay? So using the fact that we want to know the f of x plus delta x, and we know the f of x, and we know the derivative, and we know how far away we are from the value that we started. I'm talking really fast, it feels like, but I don't know why. Slow down. Easy down. All right. So we want to know the f of 26. So we all know right off the top of our head the f of 25, the square root of 25, right? And so that's good news for us. It's 5. Okay? And we just use the derivative, 1 over 2 root 25, square root of 25. Okay, we've got all that. And we multiplied it by how far away? How far is it from 25 to 26? 1 away. So this all turns into square root of 25 is 5. 2 times 5 is 10. 1/10 times 1 is 1 1/10. So we end up with 5 and 1/10. 5.1 for you decimal people out there. Okay, so that's how it works. Good? Super. Let's go a little faster now. So I know the f of 3. Don't even need to know what the function is. I know the f of 3. I know the derivative at 3. What I want to know is what's the value of the function at 3.1. So we're going to use that local linearity to make it all work out. So the f of 3.1, it's like the f of 3 plus 0.1, that's the delta x, right, is approximately equal to the f of x, which we know is 7, right, plus the derivative, which we know is 0.08, times how far we are, multiplied by how far away we are. So from 3 to 3.1 is 0.1 away. So if I do this, I get 7 plus 0.008. So I think that's 7.008. And we can do the same thing with 2.9. Okay. So the f of 2.9, that's like the f of 3 minus 0.1. So it's going to be essentially the same sort of dealio. 7, boom, 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 0.08. That's my rate of change. How far am I? Well, I'm negative 0.1 from it, so it's going to be minus. And so I'm going to end up with, I believe, 6.992. You can do the arithmetic on that one. But it's just having this formula. I would think this would be a great thing to show up someplace in a note card. But the concept is, you know, that if we know the value of the function, we know how it's changing, dy dx, multiplied by dx, that gets us to dy. So function plus the change in y tells me the new value of the function. Is that right? Is that right? Let's look at, excuse me, cover your ears because I just coughed. The graph. Use the graph to approximate the f of 1.9 and the f of 2.04. And again, we're going to use the fact that if we zoomed in really, really close here, you know, we're looking at this little tiny area right in there-ish. Right? 1.9 to 2.04. That's pretty, you know, we could get in, zoom in enough on that thing to make it appear to be straight if we wanted to. Okay? So we know the f of x, right? Okay, what do we want to know? We want to know the f of 2 minus 0.1, right? That's what 1.9 is. We know the f of x, which is apparently 1, right? 1. And the derivative, well, that's the slope of the tangent line, right? So there's my tangent line. What's its slope? Well, let's see. We're going, looks like down 1 and over 1, right? So that's a negative 1. So my slope is negative 1, and my change in x is about negative 0.9. Negative point, what did I say, negative 0.9? How about negative 0.1? Let's do that instead. So this is 1 plus negative 0.1, which appears to be about, oh, actually it's not negative, it's positive, isn't it? So 1 plus 0.1, thank you for catching that before I caught it. So many of you paused and said, I am going to send him a note right now, tell him where that is. So it's 1 plus 0.1, which is 1.1, which, you know, it's about right there, maybe. Yeah, that seems all right. And if we do the 2.04, it's just going to be the same thing. It's the f of 2 plus 0.04, that's 0.04. So it's going to be the 1 plus the derivative, rate of change, slope of the tangent line, and 0.04. So you can do the math on that one. Probably going to turn out to be about, I was guessing, man, 0.96. Okay, see how that works? So we're using the differential to approximate. So we pretend we straighten out the curve, we zoom in enough, and you know everything eventually, like the Earth that we're on, you know, the soccer field's flat, but the world is curved. So locally, things are not curvy when you zoom in far enough. Oops, and that's that. Forgot about that. And then the third part is the differential is also a mechanical system in your car. I don't actually know what it does. I think it helps when you're going around corners. I think that's what it does, so that the outside wheels turn faster than the inside wheels, so that your car actually turns. So that's about it for the day. Differentials. Okay? Have fun with them. We'll hope you learned something. We'll talk to you soon. And that's about it. Really it is. 10 minutes, 8 seconds. Thanks for watching. Tune in next time. Bye-bye.